Good morning, everyone. Welcome back. I'm Steve.
And I'm Scott.
And together we're Backyard Musings, broadcasting live Apple Valley, People's Republic of California.
And we are talking some science and technology again today.
Yes, sir.
Yeah, it's some pretty cool stuff.
Chemists at the University of Albany have developed a high-energy compound that could transform rocket fuel and make space travel more efficient. When ignited, this compound produces significantly more energy per unit of weight and volume than current propellants. For rockets, this means that less fuel will be needed to achieve the same mission duration or payload capacity, leaving more space for essential equipment and supplies. The research was published in the Journal of the American Chemical Society on May 2nd, 2025. Would you like to know more?
Quote, in rocket ships, space is at a premium, meaning volume space, right?
Yeah.
Said Assistant Professor of Chemistry, Michael Young, whose lab led the work. Going on with a quote, every inch must be packed efficiently and everything on board needs to be as light as possible. Creating more efficient fuel using our new compound would mean less space is needed for fuel storage, freeing up room for equipment, including instruments used for research. On the return voyage, this could mean more space is available to bring more samples home.
That's right.
Yeah.
The compound manganese diboride, MnB2, is more than 20% higher in energy density by weight and about 150% higher by volume compared with aluminum, which is currently used in solid rocket boosters.
And 150%.
And it's better than Top Hat Racing, 120% pure. It's better than that one.
We don't want to get sued by Top Hat Racing.
It's from Cedar Point in Sandusky. All right. Despite its potency, it is remarkably stable and only ignites when exposed to an ignition source such as kerosene.
Beyond rocket propulsion, the boron-based structure of NMB2 shows wide range of potential. Work from the Young Lab indicates it could also strengthen catalytic converters in automobiles and act as a catalyst for breaking down plastics.
Yeah. Manganese diboride is part of a group of chemical compounds long suspected to have unusual properties. Maybe it's arcane. But progress in studying them has been limited by the challenge of actually producing the material.
Quote again, diborides first started getting attention in the 1960s, said University of Albany PhD student Joseph Doane, who works with Young. Quote, again, since these essential looks, new technologies are allowing us to actually synthesize chemical compounds that were once only hypothesized to exist.
Quote, knowing what we do about the elements on the periodic table, we suspected that manganese diboride would be structurally asymmetrical and unstable, factors which together would make it highly energetic. But until recently, we couldn't test it because it couldn't be made. Successfully synthesizing pure manganese diboride is an exciting achievement in and of itself, and now we can test it experimentally and discover new ways to put it to use, end quote.
I mean, somebody's got to do it, right?
Yeah.
Producing manganese diboride requires extreme heat generated by a device known as an arc melter. To begin, manganese and boron powders are pressed into a pellet and sealed inside a reinforced glass chamber. A narrow electrical current is then directed at the pellet, heating it to nearly 3,000 degrees centigrade or Celsius, which would be over 5,000 degrees Fahrenheit for us Yanks. Right?
That's pretty hot.
That's pretty hot, yeah. The molten substance is rapidly cooled to preserve its structure. On the atomic scale, this process forces the central manganese atom to bond with more atoms than usual, creating a crowded arrangement tightly compressed like a coiled spring.
So I wonder, are they like little block packs when they cool? Or it can't be liquid, can it?
I don't know. I think it's just like a gunpowder in a cartridge, right?
It's just powder?
Well, something. Manganese is a powder material.
Boron
right?
is powder also.
Right. So just compressed in there and then fire that puppy up, I guess.
When exploring new chemical compounds, being able to physically produce the compound is critical. That makes sense. You also need to be able to define its molecular structure in order to better understand why it behaves the way it does.
University of Albany PhD student Gregory John, who works with computational chemist Alan Chen, built computer models to visualize manganese diboride's molecular structure. These models revealed something critical, a subtle skew known as deformation, which gives the compound its high potential energy.
Quote, there's this consensus among chemists that boron-based chemicals should have unusual properties that make them behave unlike any other existing compounds, said Associate Professor of Chemistry Alan Chen. Continuing quote, there's an ongoing quest to figure out what those properties and behaviors are. This sort of pursuit is at the heart of materials chemistry, where creating harder, stronger, more extreme materials requires forging brand new chemicals. This is what the Jung lab is doing, with findings that could improve rocket fuel, catalytic converters, and even processes for fueling plastics.
Young's interest in boron compounds started when he was a grad student at the University of California, Los Angeles. His project aimed to discover compounds harder than diamond. Quote, I distinctly remember the first time I made a compound related to manganese diboride, Young said. There I was, holding this new material that was supposed to be super hard. Instead, it started to get hot and changed into a pretty orange color. I thought, why is it orange? Why is it glowing? It shouldn't be glowing. That's when I realized how energetic boron compounds can be. I put a pin in it to explore in the future. Was that some kind of a term like
we'll save it for later. Pin it up on the
pin it.
like
the bulletin board.
Bulletin board,
yeah. Okay, got it. And that's exactly what we're working on now. Unquote.
Cool.
Okay.
Yeah. Hopefully, so like we talked about before, how finding water on the moon is crucial to splitting the oxygen and hydrogen for fuel, but this doesn't have hydrogen in it, so they're gonna have to take all their fuel with them on the trip.
But if it's they talked about it being compressed, right?
Yeah.
So maybe these little fuel chips or cartridges or capsules or whatever are something that they can put in a smaller space, which is what they're planning on doing. So
yeah, but they're not going to find it on the moon.
No.
So you're sacrificing
at least so far
power and space.
So far, right? The whole moon hasn't been explored yet.
Right.
So,
yeah. That's a true statement.
Could be
a true statement.
We don't find gold everywhere on our continent. So, but there are some places that there's a lot of gold. So
yeah.
Could be there.
China's got a lot. Okay, thanks for joining us. We'll see you in the afternoon.
They copied our gold. Take care, everyone. Thanks.
They stole